Today we're going to be talking about perpendicular lines. This is from section 3.4. Now, we've talked about parallel so far, but when we start to talk about perpendicular lines, we're going to need to know terms like this: perpendicular bisector. And a perpendicular bisector of a segment is a line perpendicular to a segment at the segment's midpoint. So if I have a segment here, and just because I need to name it, I'm going to call it AB. Okay? If I have a perpendicular bisector, here's what happens. A perpendicular bisector of a segment is a line perpendicular to a segment. Now, perpendicular means we're intersecting at a 90-degree angle. And I know that it's a bisector because it's going to cut this AB in half. And if I call this point C, then the definition is going to be AC is congruent to CB. Okay? Or I could say AC is equal to CB, because here I'm talking about the length and here I'm talking about the actual figure itself. So that's how this works. When I look for these theorems, or look at these theorems, here's what I'm actually looking at. If two intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. So what I am going to say is that if I've got M here, and this is a line L, and I mark these so that the linear pair of angles, they're both congruent, so it's going to look like this. So this angle here is congruent to this angle here. Then I can say from that that L is perpendicular to M. Okay? Because I know that if this is a linear pair and it's 180, then both of these must be 90 if they're congruent. Okay? Perpendicular transversal theorem. In a plane, if a transversal is perpendicular to one of two parallel lines, then it's perpendicular to the other. So these are my parallel lines here. And the way that these are marked is that one of them is perpendicular here. So N, and I'll call this P. We'll call this transversal here Q. And so the conclusion that I can make is that Q is perpendicular to P. Okay? Two coplanar lines are perpendicular to the same line, then the two lines are parallel to one another. So in this one, they've said you've got these two parallel, or these two 90-degree angles here, these two perpendicular lines. So I'm going to have R, I'm going to have S, I'm going to have T. So the conclusion that I can make is that R must be parallel to S because these 90-degree angles exist here. Okay, so that's how we use these theorems to kind of prove these different things. Okay, so when we look at a two-column proof of this, here I'm going to have statements, as you know, and here's my reasons. And what I'm going to do here is for this theorem, I'm going to go ahead, or for this proof, I'm going to go ahead and mark this up. I need to mark these lines, so this is going to be AD, and this is stuff that's given in this example, okay? This is BC. And so I am going to mark these different things. I have AD is parallel to BC, so I'll mark that with those little arrows. And AD is perpendicular to AB, so this intersects at a 90-degree angle here. And they also give me that BC is perpendicular to DC. So BC is perpendicular to DC, so I mark this here, okay? They're intersecting at a 90-degree angle, okay? And what we want to prove is that AB is parallel to DC. Well, let's even figure out if this is even logical. These are parallel, like railroad tracks. And so I have these two lines here that I'm going to try to say, hey, those are parallel. It makes sense. So let's look at this. First of all, I'm going to take my givens. So AD parallel to BC, and I've got AD perpendicular to AB, and I'm making sure to put my lines above this so I know what I'm talking about. I also have BC is perpendicular to DC, The reason I can say all this is because these are given. Let's develop a strategy. If I'm looking at this, I have parallel lines here, for sure. But remember, I've got this theorem back here that talks about if two coplanar lines are perpendicular to the same line, then the two lines are parallel to one another. Okay? So here's a transversal that is perpendicular to two different lines. So these R and S are perpendicular or parallel. I'm going to try to use the same sort of thing here when I say I want AB and DC to be parallel. If I can prove that there's a 90-degree angle that both of these lines, that AB and DC are both perpendicular to one of these transversals, then I can prove this. So let's look. If I then go ahead and say in number 2 that AD is perpendicular to DC, AD perpendicular to DC, okay? Because this is going to be by the perpendicular transversal theorem, okay? That says because AD is perpendicular to AB, so AD is perpendicular to AB, and because AD and BC are perpendicular, I can say these things. So I've got this kind of figured out to where this is the perpendicular transversal theorem. And so now I can mark this as a 90-degree angle here. Okay? So do you see how this works so far? So if I look at number 3. Number 3 says, here's where I'm going. DC is going to be perpendicular to, my mistake. Number 3 is going to say AD is perpendicular to AB. How can we say this? AD perpendicular to AB. Well, that's a given. We actually already set it up here, but I'm restating it to bring it back in so that I can step to my next part of the theorem. Okay? So now what I'm going to be able to say is AB is parallel to DC because if one line is perpendicular to two separate lines, then the two lines that we are perpendicular to must be parallel. Okay? So we can say two lines perpendicular to the same line must be parallel. Okay? Simple as that. So we proved that it was perpendicular to another one, and the transversal, if it's perpendicular to two separate lines, it must be perpendicular to the other one. One more. I'm going to start out with my givens, and my givens are going to tell me about angle E, HF. Well, I guess I should put this information in first, huh? Here's E, here's H, and here's F. Down here is G. I've got a couple angles marked as well. And so this is going to be 90. Angle here and angle here. Okay, so let's look at this. If I've got EHF congruent to angle HFG, and I'm also going to say this because it's given. EHF is congruent to HFG. They're marked, so that's given to us. In step number 2, here's where I'm going. I'm going to say that line EH, so this one here, okay, I'm going to say this is parallel to line FG. That's going to be the converse of the alternate interior angles theorem. Okay? Because if these two, take this line out of the mix for a minute. Take EF out of the mix for a minute. I've got two lines here, basically looking like this, right? Cut by this transversal. And I've got an angle here and an angle here that are congruent. Okay, so there's alternate interior angles because they're inside these two lines. So I can now mark this because these two are going to be parallel now, as we suspected before. Okay. Then in step 3, let's look at where we're going. We want EH perpendicular to GH. EH perpendicular to GH. So let's look at the way that this goes. In step number 3, we are going to use this fact here that FG, that's a line, is perpendicular to GH. That's a given. So we don't necessarily always have to use our givens first, but we're going to bring it in now because this is given. Okay, now let's look. I have two parallel lines. I have a transversal that is perpendicular to one of them. And so what I'm going to use now is, look back here for just a minute, perpendicular transversal theorem. In a plane, if a transversal is perpendicular to one of parallel lines, so if it's perpendicular to one of two, then it's perpendicular to the other line. Guys, look at this. It's perpendicular to one of them. This line here, HG, is perpendicular to okay? Let me rewrite this. GH must be perpendicular to EH. Why? Because if GH is perpendicular to one of the lines, FG, given, that is also parallel to this line, then we must have a situation where by the perpendicular transversal theorem, if it's perpendicular to one of the parallel lines, it's perpendicular to the other. Okay? That's how this works, guys. We're just using these theorems to prove other things. And so the distinctions that we make between these theorems and saying these things is subtle. Like perpendicular transversal theorem. It makes sense. If it's perpendicular to one, then it must be perpendicular to the other because they're like railroad tracks. If you cross railroad tracks at a 90-degree angle, you're going to keep walking and go across the other one at a 90-degree angle. It makes sense. We've just put words to it, okay? So keep watching. We'll see you next time.